All right, so we'll move on. And our next presentation is by Ankush Khandelwal and Xiang Li, both graduate students at the University of Minnesota. And the title of their presentation is Investigating the Role of Source Characteristics in Meta Learning, Applications to Hydrology.
Hello, everyone. Can you see my screen?
Yes.
Perfect. So yes, my name is Ankush, and today I'm going to talk about our work on using data from.
Ankush, we actually don't see your presentation. We see your Google Drive.
Let's do that again. Sorry about that. How about now?
Yes.
Much better.
Perfect. Sorry about that. All right. So yes, my name is Ankush, and today I'm going to talk about our work on using limited data from multiple sources to build more robust models. And a number of computer scientists and hydrologists have contributed in this work. And this collaboration has been really helpful for us to ask the right questions and move towards building better operational products. All right, so all right. So in many personalized prediction applications, we often face the challenge of having limited data to build models for our sources. For example, in our stream flow prediction task, we have multiple basins, and we want to build models to predict stream flow for these basins. But we have very limited data to build individual models. And similarly, we have another application where we are trying to predict lake temperature for different lakes, and we have very limited observations for individual lakes. So there is a need to combine data from these sources to build more robust models. And this challenge happens in many other applications, not just hydrology. So a very intuitive thing to do would be to just combine data from all these sources together trivially, but due to inherent characteristics from these sources, this trivial merging is not going to work because there is heterogeneity in how the input and output variables are related. For example, for the stream flow monitoring application, for the same weather driver, we could have very different runoff or stream flow predictions depending on the slope, soil properties of a basin. And similarly, let's say we are trying to predict mood of a person based on a weather event, that mood will depend on the personality of a person as well. So that's what makes it challenging to just trivially combine the data. And in this work, we are exploring source modulation as a strategy to address this challenge. At a very high level, what this is trying to do is to use these characteristics as additional features in our model. And then one of the very simple way to do that would be that you take your input data, which is X in this, the left model, and you concatenate or combine your static features with that data, and then you try to predict your output variable of interest. Another example of this modulation is EA-LSTM, which was proposed in the context of stream flow monitoring. The idea here is, at a high level again, is to change the input gate, and it uses static characteristics to modulate the cell gate of LSTM. So for this talk, you don't have to know the details of LSTM, how these gates work. It's just another way to use static characteristics to do modulation. And we are going to use this strategy for a number of our experiments. All right, so with source modulation as a key context, we are going to explore 4 key questions in this talk that are related to the role of source characteristics in these models. In the first setting, our goal is basically to build a model that's trying to predict stream flow given our weather data and these characteristics. So in some sense, we are trying to build the forward model. But the key question here is that when these characteristics are not known, let's say we don't have access to these basin characteristics, can we use random characteristics and still do modulation, right? And then in the second setting, we are more focused on learning these static characteristics given our input and output data. And let's say if we are able to learn this model, can it help us in addressing some common challenges with these characteristics? For example, can we reduce uncertainty in these known characteristics? Or can we impute these characteristics for basins where they are not available? And finally, can we discover new characteristics or meaningful characteristics when we have no idea about what characteristics are important? So we are going to explore these 4 questions in this talk, and I'm going to start with our first question. And before we go deeper into the question, let me just give you an overview of the data set that we are going to use and the experimental setup. So in terms of data, we are using 531 different basins from the CAMELS dataset, and these basins are spread across the US. And for each basin, we are given these 27 static characteristics. And these characteristics come from the climate of that region, geomorphology, and geology. A thing to remember is that these characteristics are static. They don't change over time. And in terms of input and output, we have 5 weather variables for each basin, and we are trying to model stream flow as our output variable. Now, as I said before, we are focused on source modulation as a way to handle the heterogeneity. So in these experiments, we are going to use EALSTM as a modulation strategy. And for each basin, we have 20 years of data, which we are breaking it into 10 years for training, 10 years for testing. And to evaluate our performance, we will calculate NSE value for every basin. NSE is a widely used measure in hydrology. For now, just know that higher NSE means a better prediction of stream flow. All right, so coming back to our question, as I said before, from a methods perspective, what we are given is some training years for our sources. In our case, we have these 531 basins, and we have only input and output, and we don't have access to these static characteristics. Can we still do source modulation? So that's the question that we're trying to answer. And one possible solution is to assign random vectors to these sources. So, and one way to assign random vectors is that you create values from a Gaussian distribution and map each source to a point in a d-dimensional space, right? And this d could change on number of sources and type of application that you're working on. So the core idea behind random vectors is that in absence of any information about our sources, we are just trying to assign something that has no information about similarity. Like that's one way to achieve that. Another way to do that is to just give an index to every basin, and those indexes can be converted into one-hot vectors, which makes it easy for ML algorithms to use those indexes. So again, both of these are trying to make an assumption that our basins are either equally similar or dissimilar to each other. We don't have any prior information about the similarity. And we want to see that even with this assumption, can we still do source modulation, right? Okay, so before I show you the result, on the bottom right, you can see our architecture still. We have that Z on the bottom, and we have now 3 choices of Z. First is we use the actual physical characteristics that are given from the data set. So we will compare our results to that. And then we have 2 options. One is we use the Gaussian random vectors. In this case, we chose the dimensionality to be 512. And the other choice is we use these one-hot vectors. And here the dimensionality is 531 because for one-hot vectors, the dimensionality matches with your number of sources. So we have these two choices of working without actual characteristics. Now, if we look at the results, what we found that these random vectors perform comparable to actual features, which was very surprising to us. So let me explain you this this plot. So each dot on this plot represents a basin. So we have 531 such basins, and the axis represent the NSE values when we build that source aware model. And we have, as I said, we have different choices for Z when we learn that source aware model. So on the x-axis, it shows the NSE values if we use the actual characteristics given from the camels dataset. And on the y-axis of the left plot, you can see the performance when we use Gaussian random vectors as source characteristics in the model. And you can see that the results are pretty much on the diagonal, which suggests that random vectors and also one-hot vectors are just as effective as physical characteristics in terms of source modulation. So what this kind of tells us that if we are in a situation where there is source heterogeneity, but we don't have access to characteristics, using these two random vector strategies will already take us pretty far. And a very obvious question that comes after this is, what if this is just limited to camels data set? So we did the similar experiment on lake temperature data set, and we found similar pattern that these random vectors were performing comparable to using physical vectors. Then the follow-up question could be, what if these specific settings that we used in these experiments were the reason why we got similar performance? So we did experiments on the different data sparsity settings and used different modulation strategies as well. And we found that these vectors, or this random vector strategy, is robust across a number of different settings. All right, to summarize, when our focus was on building model to predict stream flow, we could use random vectors and get a decent start. Now we are going to switch to the other strategy or other question, is that if our focus is on building a model that can learn static characteristics, can that model address some key challenges about these characteristics, right? So at a very high level, from a modeling perspective, what we're looking for is a model that can take this time invariant data, which is my weather drivers and my stream flow, and learn these time invariant characteristics about my sources, right? So taking time variant inputs and learning time invariant characteristics. And with that model, we will try to answer these three questions. So before we jump into these questions, let me give you an overview of the approach that we have taken to build such an inverse model. And there could be a number of different ways to do it. But in this work, we are exploring representation learning as a way to address this model formulation. So again, at a high level, what we are trying to do is build a neural network that could learn these source specific embeddings from the data. And the key idea behind this learning strategy is that if I take any two samples, time series samples from a basin, the embeddings that come out of it should be very similar. In fact, they should exactly be the same. That's what we want. We want these embeddings to be time invariant. So if you look at this figure, AI and PI are the two samples coming from the same basin, right? But if you take two samples from two different basins, for example, AI and NI, we want the distance between those two embeddings should be high because they are from a different basin. And this notion can be very well captured by contrastive loss in general, which is a very popular learning strategy in self-supervised learning these days. And similarly, we could add more regularization to this network. For example, we could force these embeddings to reconstruct the data that was fed in And finally, if in some situations we have access to these characteristics, but they could be uncertain or incomplete, we could use those as further constraint to make these characteristics more meaningful and learn more generalizable patterns. So that's the overview of the representation learning model that we are assessing as a solution for inverse modeling. All right. With that background, now let's start looking at these questions. So the first challenge that we're trying to analyze is that we have these z values, we have these static characteristics, but there is uncertainty in them, which is a very common problem in hydrological applications. Again, we are going to use CAML's dataset to analyze this scenario. So what our hope is that because we are learning a model that is using all the basins together, it will learn generalizable patterns and might be able to reduce uncertainty in some of these characteristics. So to simulate this setting, what we did is we took the characteristics from the CAML's dataset and randomly corrupted 10% of them in this setting, and we added one standard deviation noise in those characteristics. For example, here you can see this 531 cross 27 matrix. So 531 stands for our 531 basins, and 27 is our 27 characteristics. And these yellow cells represent the values that were corrupted. And on the right, you can see an example of that corruption for one of the characteristics, which is elevation mean. So on the x-axis, you can see the true values, and on the y-axis are the corrupted values. Now to evaluate our model, we will look at the RMSE values with respect to the actual values. So for example, in this case, the RMSE of corrupted values with respect to actual values is 0.83. So after we are done building a model, would our reconstruction lead to less RMSE? That's what our goal is. So in terms of the model, or in terms of our characteristics, we have these choices. First is the true characteristics that we are going to use as a reference. And then we have these corrupted characteristics that I just explained. And then what we want to test is, if let's say in real world, somebody gave us those corrupted characteristics as reality, and we build this representation learning model, how well it will be able to reconstruct, and would that reconstruction remove some of those errors? So that's what we want to do. To repeat, when we are building this model, we are going to use these corrupted characteristics to minimize the loss, not actual characteristics, right? And then we want to compare these reconstructed characteristics, how close they match with the true characteristics, right? And in order to make sure that we are not overfitting, we again divide the data into two phases. When we are building the model, we use training years, and when we are reconstructing using our inverse model, we use some other time period. All right. So now this plot kind of compares our performance across all 27 variables. So the x-axis, you can see the name of the individual characteristics, and the y-axis shows you the RMSE, and the blue squares here represent the RMSE after corruption. So comparison of actual characteristics and corrupted characteristics. And the green dot represents our reconstruction after our inverse modeling process. And you can see that across almost all of these variables, we are significantly reducing the RMSE, which suggests that because we are learning a single model, it is able to learn generalizable patterns to remove those measurement errors from our static characteristics. All right. So now we are going to move to our second challenge, where Z is available for some basins, but it is not available for the others. So this is how it looks like from a modeling perspective. We have some training basins where we have access to both X, Y, and also our static characteristics. But then there are some basins where we don't know those characteristics. So can we learn a general model that could impute or could generate characteristics for those testing basins? So again, we are using the CAMELS dataset for this experiment. And we divided the data into 400 basins for training and then 131 basins for testing. And remember that when we train, we use the training years for training. And when we test on the testing basins, we use the testing years. So this is a very, very extreme out of sample test in some sense, where those testing basins were not seen during training. And that training, the period on which we are testing, was also not seen during training. All right. And to compare, now we are going to look at the actual values for these basins versus what we predict from our representation learning model. So here is the scatter plot for those 27 characteristics. So there are two main observations that you can see in these results. First is that a lot of these features, for a lot of these characteristics, the points are along the diagonals. That means that we are able to do a very good job of predicting those characteristics. And for some, we see that the results are suboptimal, or there's more variation in those results. So the possible reasons for those poor predictions could be that for those characteristics, weather and stream flow does not uniquely identify that relationship. So there is no way we can learn it from the data, or that our ML architecture right now might have some limitations that's not allowing us to learn those characteristics. So these are some of the questions that needs to be explored further. But even at this level, we can say that representation learning does have the potential to learn a generalizable function to impute characteristics for unseen basins. All right, so finally moving to our last challenge. So here we not only have access to the values of characteristics, but we don't even know what those characteristics are. So in this setting, how can we learn any meaningful characteristics about our sources? So again, from a model perspective, we have some basins for which we have only, basically for all basins, we have only X and Y, and we have no information about Z. So if you look at our representation learning framework that I showed before, out of the 3 loss functions, we cannot use loss function that was driven by knowledge of these characteristics. So we are going to rely only on triplet loss and reconstruction loss. So in some sense, now we are working in a self-supervised representation learning setting. Now to evaluate such an embedding, what we did is we compared the basin similarity when you use physical vectors that were given from CAMELS, and we compared basin similarity when we use our learned embeddings from this model. And to visualize that similarity, we just calculated the Euclidean distance between every basin pair, and that's what you're looking at in these matrices. So basically there are 531 rows and 531 columns, and each cell represents the distance between those two basins. And basically the lower color means that those basins are similar with when we look at physical characteristics. And if you look at the matrix generated from learned embeddings, you can see that there is a similarity pattern in these embeddings, and it looks similar to what we see in physical features as well. So this already shows that there is a promise in learning embeddings that might have physical meaning as well from this representation learning strategy. All right, to just summarize, what we did is we analyzed source modulation as a strategy to handle heterogeneity in our sources. And we answered 4 questions related to source characteristics. And we learned that random vectors is a very viable way to do source modulation when you have no idea about these characteristics. And when our focus is on learning and learning more about these characteristics, representation learning is a very promising solution to address uncertainty and to impute characteristics and also discover unknown characteristics. So in terms of future work, source modulation can be seen as one of the ways of doing meta learning, where we are trying to build individual or specific models by modulation for every basin. So we are going to compare whatever we have learned here with other meta learning strategies. And as I said before, representation learning is one way to address this inverse model scenario. And there are other ways to do representation learning as well. So we are actively working on those new possibilities. So thank you for your time. I'm happy to take some questions.
Yeah, I think, thank you, Ankush. I think we're over time now, so we're going to have to take a break because